Good afternoon, everyone. I'm Donghao Yang, and I'm excited to share our work titled Enhancing Automated Program Repair with Solution Design. First, let me provide some background on our research. The issue lifecycle for open source software tends to be quite lengthy. We investigated two large open source projects, Flink and Solar, and found that the average handling time for Flink is 42 days, while for Solar, it is a staggering 183 days. Such extended cycles introduce numerous risks. Meanwhile, existing automated code maintenance tools often fall short, frequently failing to generate applicable patches, so most maintenance still requires manual work, which doesn't help reduce delays. To address these problems, we first analyzed the process of resolving issues in the open source community. We found a typical pattern. First, an issue is raised. Second, maintainers engage in online discussions to find a solution. Third, they assign the task to a developer for patch implementation. Finally, the developers submit patch for code review. Notably, in this case, the discussion and review phases only take about 2 days, while programming consumes around 20 days. Clearly, reducing programming time could significantly shorten the issue lifecycle. We also noticed that discussions contain rich information, such as analyses of bugs and debates over solutions. Maintainers can leverage these discussions to guide themselves in implementing high-quality patches that align with multiple stakeholders' interests, which is crucial for passing peer review. Inspired by these, we aim to leverage the content of human discussions to enhance the issue-solving process in the open-source community. We use an example of Flink 32976 to demonstrate our idea. The solution is highlighted in blue stating, "Therefore, we can easily fix this issue by adding a check." The arguments are highlighted in green, including interpretations of the error's cause and agreement from other maintainers. The final commit is based on the solution, but differs from the check mentioned in the solution, indicating that there remains a gap between the solution and its implementation. To avoid the distraction of irrelevant information in discussions, we focus on extracting the solution and related arguments, combining them to drive a large language model in generating high-quality patches. Now, let me introduce our approach, DRCodePilot. In the first step, we use drMiner to extract solutions and arguments from discussions. drMiner is another project of ours, and I encourage those interested to check out Zitian Yang's presentation at the Code and Issue Report program. drMiner first identifies design-related sentences in the discussions, then pairs solutions with arguments to be complete design rationales. In the second step, these design rationales guide GPT-4 in identifying defect code segments and generating patches. To ensure that the patches are well suited to the project's codebase and easier to pass review, we optimize them in subsequent steps with 2 types of information: project-specific knowledge and identifier recommendations. For project-specific knowledge, we fine-tune the Code T5P model on the project codebase and use it to create patches that reflect common practices for the project. Then, we recommend alternative for identifiers in the patches to reduce the likelihood of compilation failures due to incorrect functions or member variables. Specifically, we extract functions from the project codebase to train Code T5P 220M. We mask some portions, prompting Code T5P to predict the masked content. This allows Code T5P to learn project-specific knowledge and provide valuable reference patches. As for identifier recommendation, we first find code segments that are logically similar to the patches, then establish recommendation relationships based on cosine similarity. We particularly recommend identifiers that only appear in the patch and not in the codebase files, as these identifiers are more prone to errors. Finally, in the 5th step, we provide the feedback from the previous steps to GPT-4, allowing it to output optimized patches in conjunction with the discussion history. Next, I will discuss our experimental analysis. We explored 3 research questions. comparisons with baseline models, ablation studies, and experiments that combine design rationales with other large language models. To achieve this, we developed a benchmark by selecting issues from the open source systems Flink and Solr on Jira. This process ensured that we comprehensively collected metadata from the issue logs and associated these issues with relevant GitHub pull requests, PRs. We focus on Flink and Solr because they are large-scale software systems and are actively tackling a wide array of issues. We established a benchmark that includes 938 function-level repair cases. Our filtering criteria align with Defect4J, ensuring consistency and relevance. The benchmark features fixes for Java source files, and we narrowed our scope to focus on changes in only one source file, with a maximum change threshold set at 22 lines. We chose full match and CodeBLEU as our metrics. On one hand, we couldn't establish a benchmark based on execution, since most unit tests fail to run due to dependency error. On the other hand, we focus more on the quality of the patch, as high-quality patches are essential for receiving reviewer approval in the open source community. And passing mere test cases doesn't guarantee optimal solutions. In comparisons with various advanced code models, DRCodePilot demonstrated outstanding performance, improving by 4.7 times on Flink and 3.6 times on Solr for full match. As for CodeBLEU, the scores increased by 5.4% and 3.9% on the Flink and Solr datasets, respectively. In the ablation experiments, removing design rationales led to a decline in full match patches by 81.65% and 94.44%, indicating that integrating design rationales into the patch generation process significantly enhances patch quality. The impact of removing identifier recommendations was also notable, highlighting that even advanced code models may generate incorrect identifiers when fixing issues. In contrast, the effect of removing reference patches was relatively minor, likely because the simple models used for reference patches offer limited help to GPT-4. We further explored the application of design rationales across different size models, analyzing them from three perspectives. First, we verified the enhancement effects of design rationales on different large language models. Second, we compared the improvement of manually annotated design rationales with those extracted by tools. Lastly, we examined the effects of directly inputting all developer discussions into the model. From the benchmark, we selected 61 cases with rich discussions and invited 16 participants with relevant expertise for annotation, including professors, students, and engineers, to ensure high-quality design rationales. First, design rationales significantly enhance the performance of various models. Stronger models benefiting even more, likely due to their better understanding of the content of design rationales. Second, manually annotated design rationales showed a more substantial improvement effect compared to those automatically extracted by tools. This indicates that future optimizations of extraction tools could help close this gap and improve the efficiency of utilizing design rationales. Finally, directly inputting all discussions into the model also significantly improved repair performance, but surpassed by utilizing design rationales in generating fully matched patches. This suggests that advanced models like GPT-4 can absorb useful information from developer comments, but still disrupted by noisy content. Next, we move on to the discussion section of this paper. The experimental results indicate that our method effectively bridges the gap in the last mile of patch generation discussions. Compared to traditional manual programming processes, DRCodePilot can generate high-quality patches in a shorter time, significantly reducing time cost of maintenance. To gain a deeper understanding of the strengths and weaknesses of DRCodePilot, we selected 36 fully matched cases and 36 cases with low CodeBLEU scores for in-depth analysis. The results show that DRCodePilot performs exceptionally well in scenarios with rich discussions, while its performance declines in the absence of discussions or when discussions are poorly documented. Additionally, we found that the understanding of certain design rationales relies on external information, such as error highlights, without clear expected behaviors. URL references involving key details, e.g. a URL for another issue link 27487, and mentions of the toString method without actual content. In these cases, due to a lack of corresponding background knowledge, the model may struggle to accurately comprehend the design rationales. Looking ahead, we plan to further improve DRCodePilot in 3 areas. 1. Enhancing the capability to extract solutions for more targeted guidance. 2. Providing external information support for design rationales to help the model better understand contextual knowledge. And 3. Developing it as a tool for the open source community, envisioning a scenario where large language models can capture design rationales in real time during discussions and generate patches, thus achieving an efficient human-machine collaboration. That's all. Thank you. Please feel free to ask any question.